This is chapter 5, question number 69. It says a 3 kilogram box that is several hundred meters above the Earth's surface is suspended from the end of a short vertical rope of negligible mass. A time-dependent upward force is applied to the upper end of the rope and results in a tension in the rope of T of T equals 36 newtons per second times time. The box is at rest at T equals 0. The only forces on the box are the tension in the rope and gravity. Question A, what is the velocity of the box at 1 second and 3 seconds? So first to start, we'll get our free body diagram. Just got our box going down, mass times gravity, going up is our function T equals 36. And it's newtons per second times time. Kind of odd, but we'll go with it. And from this diagram, we can set up our equation that mass times gravity minus our function T of T is equal to mass times acceleration. So now we're going to take this equation and solve for acceleration, because what we're going to do is we're going to get our acceleration equation and take the integral of that to get our velocity equation, at which we can then use to solve question A, getting our speed at specific times. So, see, you check my notes, sorry. It's really easy. You just divide by mass. You divide by m, move it over. I'll just erase that. So our acceleration equals this. Now to take the integral of it, we're going to be taking the integral of it as with respect to t. But I should simplify this a little bit more before we get there. Sorry, I'm just jumping way ahead of myself. Let's see, so these cancel for that term. So you're going to have g minus t of t over m. And then here you have a number for t of t, and you also have a number for m. It's 36 for t of t. Your mass is 3 kilograms. So that comes out to just 12 newton. So it's newtons per second per kilo or times kilogram now. With G minus 12 newtons. Say again, times kilogram times time. So all that is still times time. Fun stuff. Now we can take our integral with respect to t. So we're going to get b of t equals g times t minus 12. And I'm not going to put those units there because there's so many of them. But t turns into t squared over 2. And now that we're here, we can just plug in our numbers. So at 1 second, plug in your, and this is 9.9, 9.81, 9.81. Plug in your 1, and it comes out to 3.8 meters per second. So velocity 1, 3.8 meters per second. Then velocity of 3, I believe is the next one, comes out to negative 24.6 meters per second. So that's question A. So the next part of this problem is question B. It says, what is the maximum distance that the box descends below its initial position? So if we take our velocity function and we find the zeros of that, let's say the 0 Let me erase this so we have some space. So let's see, if our position, how I explain it, when your velocity is 0 and it's gone from negative to positive through your function, at this point is when it has gone down low enough and it's coming back up at its lowest point. So in order to find the zeros, we just take our velocity equation, v of t equals, I'm just going to put 9.81 times t minus, then I change 12 over 2 to 6, t squared. You can take that, find your zeros, take out a t, so we have negative 6 times t plus 9.81 times t. So your zeros are going to come out to be 0, but then also 1.635. So 1.635 seconds is when the box reaches its lowest point and it starts coming back up. The next question, question C, is at what value of t does the box return to its initial position? So again, we're going to be finding the zeros, but of a different function. So we're going to take the integral of our velocity function to get our position function. So r of t would equal 9.81 t squared divided by 2 minus 6 divided by 3 t to the third. And you take the zeros just the same way. You'll have a t squared times negative 2t plus 9.81 over 2. And when you solve that, you obviously still get 0 for one of your zeros, and the other is 2.4525 seconds. So at 2.45 seconds is when the box returns to its initial position. And that is question 69.